Hello everyone, welcome to the OneClass channel. My name is Marlyn. I'm a second year student at the University of Waterloo. I'm studying chemical physics with a minor in math. Today I'm going to be going through some high school level and college level calculus problems. Be sure to check out the links in the description if you're in need of any extra homework help or like some one-on-one tutoring. Okay, so for our first question, we're going to be calculating the curl and divergence of a specific vector field. And so, in order to do that, I need to figure out what curl and divergence are. So just 1 moment. Okay, so divergence is defined as the dot product between the gradient vector and the vector field. So the gradient vector you can think of as an operator, and it is equal to the partial derivatives in however many coordinates you have. So since f is using x, y, z in rectangular coordinates, I'm going to have 3. And then my function is going to be, let's call it f1, f2, f3. And so my divergence is going to be the dot product between these two. And that is going to be the partial derivative of f1 with respect to x plus the partial derivative of f2 with respect to y plus the partial derivative of f3 with respect to z. And what is actually going on, so this is the math of what the divergence is. What that actually means graphically is, let's look at what different divergences of functions would look like. And so let's say we have the vector field xy. So the divergence of this vector field is going to be, since it only has 2 coordinates, it's going to be the derivative of f1 with respect to x plus the derivative of f2 with respect to y. And that is just going to give me dx over dx plus dy over dy, which is 1 plus 1, giving me 2. And so in this case, I have that the divergence of my vector field is over 0. And if you actually plot what the vector field is going to look like, let's just slowly draw that out. You get a plot that looks like this. And how I know that is, let's say I have the coordinate 0, 1 here, for example. Since my vector field is xy, it will give me a vector that is 0 in the x direction and 1 unit in the y direction. And here you can see if this is 0, 2, it'll be 0 in the x direction and 2 in the y direction. And so you're going to have something similar here. You'll have an x and y component for these vectors and so on and so forth. And so that's just how I got to drawing out the vector field. And so I can see here that if the divergence is over 0, the flow of the vector field looks like it's going away from the center. And so let's say I had an upside down cup, for example, and I pour water over it, the water would flow away from the center of the cup. And so that's what this is describing. Let's look at what a divergence less than 0 would give us. So as an example, let's take the vector field negative x, negative y. And so its divergence would be -1 minus 1, giving me -2. And so it's less than 0, as I can see here. And if we quickly draw it out and compare with the first one, so I'm drawing out the vector field now, I will see that it actually has opposite behavior. And so it looks the exact same, but things are coming in. And so I can see that a divergence of less than 0 tells me that the flow is inward. Over 0 tells me that the flow is outward. And lastly, a divergence of 0. So as an example, the vector field -yx. So the derivative of this with respect to x is going to be 0 plus the derivative of this with respect to y, which is going to be 0. So it's going to give me that the dot product here is equal to the 0 vector. Sorry, is equal to 0, scalar. And when I actually draw this one out, I will see that it tells me that the flow isn't necessarily inward or outward, which is why the divergence is going to be 0. And so what this one actually looks like is like this. And so this tells me that it isn't moving inward or outward, it's just moving around. And so that's what the divergence tells you. And so let's go ahead and calculate the divergence of our function. And so our function is equal to x, y squared, z squared, x squared, y, z squared, x squared, y squared, z. And so the divergence, which is the dot product between these two, is going to be the derivative with respect to x of f1. So x, y squared, z squared, plus the derivative of f2 with respect to y. So x squared, y, z squared, plus the derivative of f3 with respect to z. And so the derivative of this with respect to x is just going to give us y squared, z squared, plus this one with respect to y is going to give us x squared, z squared, plus this one with respect to z is going to give us x squared, y squared. And this is what the divergence will be. And so for this one, we're going to see that for certain values of x, y, and z, it can be negative, 0, or positive. Now let's begin talking about the curl. So the curl is similar, and it is going to be defined as the cross product between our gradient vector and our vector field. And so if we define f again as f1, f2, and f3, we get I, j, k. The gradient vector comes first, and so I just put it in. And then I have f1, f2, and f3. And remember that for dot product, the order like whether it's f dot the gradient vector or the gradient vector dot f, I would still get this. For the cross product, we know that it matters, and if I switch them, then I'm switching these two rows, which would give me a different answer. And so this will give us I hat into df3 over dy minus df2 over dz minus j hat into df3 over dx minus df1 over dz plus k hat into, so these two, so df2 over dx minus df1 over dy. And so if I put that all into one vector, that will give me df3 over dy minus df2 over dz in my I component, df1 over dz because of this minus. So minus by minus is positive, this one becomes a negative. So it'll become df1 over dz minus df3 over dx. And then in my last component, I'll have this. So df2 over dx minus df1 over dy. And this will be my answer for the cross product between the two. Now what it tells us is going to be it also tells us something about what's going on with the vector field. And so let's check out three cases. And so we begin with a curl over 0. As an example, we can take if we had a curl of 2z hat. So if you did all of this and you got that in this part, you have 2. So it's over 0. When we graph it, we will see that it has behavior that we have indeed seen before, but labeled with a divergence of 0 instead. And so a curl of over 0 is going to be anti-clockwise. And it's going to be the last case that we saw before. And this is what it's going to look like. And so this tells us that a curl of over 0 will always be anti-clockwise. And that means that the curl is giving us the rotational properties of our vector field. And so if you imagine the z-axis coming out at you, this means that we have the vector field rotating anti-clockwise around that z-axis that is coming out at you. Let's check out a couple more cases. So curl of less than 0, so let's say you calculate it, and you get negative z hat. When you draw it out, that will of course be the opposite, meaning that we will get a clockwise vector field. And then lastly, let's check out the last case of a curl of 0. And this would mean no rotational properties. And so you're going to have cases where the divergence is non-zero and it's flowing inward or outward, but not necessarily rotating in any direction. So you can have, let's say it's pointing out. So for this vector field, if you calculated the curl, you'll get our curl of 0. And so now let's calculate the curl of our vector field specifically. So let's just write out, you have two options with the curl. You can write it out. So the ijk and then find the cross product, or you can just write down the formula, which would be easier if you're trying to do it quickly. Because if you do this, then you're prone to making mistakes, especially if you're in a hurry. And so it is df3 over dy minus df2 over dz, df1 over dz minus df3 over dx, and lastly df2 over dx minus df1 over dy, I believe, yeah. And so with our vector field, that is x, y squared, z squared, x squared, y, z squared, and lastly x squared, y squared, z. Let's just put in everything. So the derivative of this with respect to y is going to give us 2yx squared z minus the derivative of this with respect to z, which will give us 2x squared yz. Let's just write them in the same order. 2x squared yz. And that's going to be my x component. And then I look at f1 and take the derivative with respect to z again. So that is going to be 2xy squared z minus the derivative of this with respect to x, which will give me 2x. Let's just restart really quickly. So the derivative of this with respect to y is going to give us 2x squared yz minus the derivative of this with respect to z, which will give us 2x squared yz, comma, the derivative of this with respect to z is going to give us 2xy squared z minus the derivative of this with respect to x, which will again give me 2xy squared z. And then lastly, the derivative of this with respect to x, which will give me 2xyz squared minus the derivative of this with respect to y. So minus 2xyz squared. And so for all of them, I can see that they're equal to what I'm subtracting. And so this will give me 0, 0, 0. And this is the 0 vector. And so as my final answer, I see that in the first case, I have a non-zero divergence that is going to be this, and for my curl, I have a 0. So it's going to be a vector field with no rotational properties, and it will be flowing inward or outward depending on the value of x, y, and z. And those are going to be your final answers. Let's see if we can quickly plot it. Oh, it has an issue plotting because of all of the powers. But if you do manage to plot it, be it on your own or on a calculator, you will see no rotational properties and it flowing inward or outward depending on the value of x, y, and z. And that's it for this question. Okay, next up, you're going to want to linearize a certain function at a is equal to 16. And so let's go about doing that. So the general formula for this one is that the linearization at a point a, b of a function that takes x and y coordinates is going to be the function evaluated at a, b plus the derivative of the function with respect to x evaluated at a, b multiplied by x minus a plus the same thing but with respect to y, and that is going to be y minus b. And this is if you have a 3D function. And so you have z is a function of xy, which is equal to fxy. If you have a 2D function, like we do here, then you will get that it is equal to the function with respect to a plus f of x, a, b, x minus a. And so what exactly are we doing with this linearization? What we are doing is we are approximating the function based on the slope at a given point. So what that looks like graphically would be, let's say I have a parabolic function like this one, and let's say I want to find the value of this function at this point, which I will call a. What I will do is I will take the derivative at that point, so I find the slope, and so for anywhere within this tiny box here, if I use this equation, so if I use the slope in order to find the value, I should get a value that is close enough that I can call it an approximation. And so the blue line is called the linearization. Sorry, let's use a different color. Okay, so the black is called the linearization. The region inside the blue is my good approximation region. And the red, of course, is my function. And all of this is actually derived from Taylor series that tell us that we can write f of x as a summation of the function to the nth derivative evaluated at a over n factorial multiplied by x minus a. And so that's exactly what you're seeing here, except that instead of writing out the entire function, why we call it a linear approximation is because we're going to actually cut this off at n is equal to 1. And so we'll only have the function evaluated at 0. Sorry, the derivative of the function, the 0th derivative of the function evaluated at a over n factorial, x minus a, plus the first derivative evaluated at a, x minus a over n factorial. And so if you do that is where you would get this formula from. Okay, so next up, let's try and find what we need for our function. And so if this is the formula, we need to find the derivative with respect to x. And so we know f of x is equal to x to the power 1 over 2. So the derivative is going to be equal to, we're going to use the exponent rule, and that just states that d over dx of x to the power of a is equal to 1 over a x to the power of a minus 1. And so with 1 over 2, it's going to be 1 over 1 over 2 x to the power of 1 over 2 minus 1. 1 over 1 over 2 is going to give us 2. X to the power of 1 over 2 minus 1 is negative 1 over 2. And this will give us 2 over root x. Sorry, this is supposed to be a. My apologies. Ax, a minus 1. Okay, and so let's just run through that again. This will become 1 over 2 x to the power of 1 over 2 minus 1, which is 1 over 2 root x. Okay, and then our function evaluated at a would be root a. And so when we put that all together, the linearization of the function at a is going to be root a plus 1 over 2 root x into x minus a. And so if we want to use the point 16 is what we're using as our point, it would be root 16 plus 1 over 2 root 16, x minus 16. Since that is our point. And this will give us 4 plus 1 over 8 x minus 16, which should give us 4 plus x over 8 minus 16 over 8. This is going to give us minus 2, so 4 minus 2 is 2, leaving us with 2 plus x over 8 is going to be our linearization at a point near that 16. And so if we want to find, for example, the value of our function at 16.1, because 16.1 is going to be within this good approximation region, so you're going to choose points that are close to 16, be it before or after, as long as they're not too far from 16. Then at 16.1, our example, sorry about that. It's going to be 2 plus 16.1 over 8. And this is going to give us 4.0125. So this is our approximation of what the function is going to be. Let's check out what the function actually is. And so the function at 16.1 is the root of 16.1. And that is 4.0124805.3. And so you can see that if we had rounded it off, we would have gotten the exact same thing, and that the error is really, really small. And so that's just how all of this works. Your final answer should be this function, 2 plus x over 8. Okay, next up, sorry, just one moment. Sorry about that. So for our next question, we're looking for the integral of cos squared x. And so we're going to be using just a definition of what an integral is in order to understand how to integrate this. And so cos squared x is a function that is hard to find the area under the graph because of this squared term. And we can see that even if you make the substitution, so let's say we tried to find this using substitution, and we chose u is equal to cos x, that would mean du over dx is negative sine x, which means dx is du over negative sine x. And so if you substitute this all back in, you'd get the integral of u squared du over negative sine x. And so substitution obviously doesn't work. This square term is making things hard for us. And so it makes the most sense to try and find a function that is going to be equal to cos squared x, but not have a square term in it, and integrate that instead. And the reason that that makes sense is because what an integral is. The integral is the area under the graph. And so let's say I have two functions. I have a function a of x and b of x. If both functions are the exact same, which means that when I plot them, the area under the graph for both of them should be the same. Let's say this is ax and bx is the exact same. That means the area under the graph would be the same. And so writing that down mathematically, that means the integral of ax dx will be equal to the integral of bx dx. And so this does make sense. And so now let's go about finding a function that is equal to cos squared x, and we're actually going to use an identity. And so if we can remember that cos 2x is equal to 2 cos squared x minus 1, we will get that cos squared x is equal to cos 2x plus 1 all over 2. This is much easier to integrate. I don't have any square term disturbing me. And so let's just write that down. The integral of cos squared x dx is equal to the integral of cos 2x plus 1 all over 2. And then now we're going to use some integral properties. Okay, and so the first one that we'll be using is going to be that the integral of a constant a by a function of x dx is equal to the same thing as if you pulled out that constant and just had f of x dx. And to just show you that, let's say my function is 2x and I'm trying to integrate from 0 to 5, right? If I instead just had the function x, integrated it, and then multiplied it by 2, so from 0 to 5, that's going to be 2.5. Multiplied it by 2, I'd get 5. But if I integrate 2x, I would get from 0 to 5, and I have 5 to 10, and then I divide that by 2. But I get the exact same answer as I would if I just integrated the x and then multiplied that by 2, which is why this rule holds. Next up is going to be that the integral of f of x plus g of x dx is the same thing as if I integrated them separately. And again, that is just off of what an integral is. I'm taking the area under the graph. If I add two functions and take the area under that total graph, it's the same thing as taking the area under those individual functions and then adding them together. And so now when I apply that to this, I'll use my first rule to pull out that 1 over 2. And this will become that the integral of cos squared x dx is equal to 1 over 2 multiplied by the integral of cos 2x plus 1. And then I'm going to use that second rule we just talked about for if I have two functions. So my two functions are 1 and cos 2x. So just apply property 2. And this will become 1 over 2 multiplied by the integral of cos 2x dx plus the integral of 1 dx. This integral is quite easy to solve. We know that it's going to be x. The cos 2x, let's go about solving that. So the integral of cos 2x dx. We're going to make a substitution and choose u is equal to 2x, which means du over dx is equal to 2. So dx, what we're going to substitute for dx is going to be du over 2. So let's go ahead and put that all in, and we'll get the integral of cos u du over 2. Pull out the 1 over 2 using the first property we talked about. And we know that the integral of cos u is going to be sine u. So this will become 1 over 2 sine u plus c, but we're going to add the plus c at the end. So this will just become 1 over 2, substitute back in your 2x, sine 2x. And so when I put that all together, I'll get that this is equal to 1 over 2 into 1 over 2 sine 2x plus x. Now I just expand that to get 1 over 4 sine 2x plus x over 2. And then now I add the c. So plus c. And let's just make this all a little bit cleaner. And this is going to be our final answer. Let me just demonstrate that cos squared x is indeed equal to what I wrote it down as. So that's going to be cos squared x plus 1. Let's put that all in brackets. And then put that all over 2. And you can see that they are directly on top of each other and the two functions are equal. So when I integrate one, the answer will be the same as if I integrate the other one, because the area under the same function is going to give you the same answer. And that's going to be it for this question. Okay, next up, we want to integrate cotangent squared. So let's go about doing that. So we're going to use the same methodology as last time, because again, we want to get rid of the squared. And so the first rule that we will be using is that if a of x is equal to b of x, then the integral of ax dx is equal to the integral of bx dx. This is the first rule that we're using. And then we need to find what cotangent squared is equal to. And we find that cotangent squared x is the same thing as cosecant squared x minus 1. And so we have made it easier. We have a minus 1, but we still have this squared term that is disturbing us. So first, let's just write out what we have. Is equal to the integral of cosecant squared x minus 1 all over dx. And then let's use another integral property that we previously talked about, which states that the integral of f of x plus g of x dx is the same thing as if you took their integrals separately. And so let's apply that to split this up. And this will give us the integral of cosecant squared x over dx minus the integral of dx. Okay, and then next up we're going to need to figure out how to solve this, and we're going to use substitution. there is the generally known answer for the integral of cotangent squared x. I'm just showing you how to get there. And so in order to get there, we're going to use a substitution that is well informed. It's not just a guess. And we're going to substitute in cotangent x. Now to find the derivative of cotangent x, so du over dx is going to be equal to d over dx cos x over sine x. Let's go ahead and find that using the quotient rule. And I'll just write that down for you. F of x over g of x is going to give me the derivative of f multiplied by g minus the derivative of g multiplied by f all over g of x squared. And so if f of x is equal to cos x, the derivative is equal to negative sine x. G of x is equal to sine x. The derivative is equal to cos x. And so we're just going to put that all back in. And we find that the derivative of cotangent x is going to be negative sine x by sine x minus cos x by cos x all over sine squared x. Let's just erase everything we wrote below to get there. Okay, and then we're going to simplify this. And we're going to pull out the, let's write it out. So this becomes negative sine squared x minus cos squared x over sine squared x. And then we're going to pull out this minus 1 in order to make this an identity that we're more familiar with. So minus sine squared x plus cos squared x all over sine squared x. This identity says that this is equal to 1. So this will become negative 1 over sine squared x, which is negative cosecant squared x. And so we have, let's just write that in, that the derivative of cotangent x is negative cosecant squared x. And we can erase all of that side work. Okay, and so this will give us that dx is equal to du over negative cosecant squared x. And so when you put that all in, you'll get that the integral of cosecant squared x, and then you substitute in dx. So du over negative cosecant squared x. These two will cancel, which will just leave you with the integral of negative du, which is negative the integral of du, and that's just going to give us negative, the integral of du is u, so negative cotangent x is going to be your answer for that. And then the integral of dx is just x, as we know. And so for our final answer, we'll get that the integral of cotangent squared x dx will be negative cotangent x minus x plus c. And that is what your final answer is going to be. Okay, next up we want to evaluate the iterated integral by converting everything to polar coordinates. And so let's go about doing that. Okay, so for this question, first up, we know that, let's just write down our conversions very quickly. R is equal to root x squared plus y squared. x is equal to r cos theta, y is equal to r sine theta, theta is equal to the inverse tan of y over x. So we're going to use these conversions in order to convert our iterated integral to polar coordinates. That will make the integration part a lot easier. And so first we can already spot this in our integration. So that means that instead of integrating x squared plus y squared over dA, that means I'm integrating r over dA. I also need to note what dA is in polar coordinates, and dA in polar coordinates is r dr d theta. And then lastly, I need to convert my integration bounds. And so from x is equal to 0 to x is equal to 2, when x is equal to 0, that means r cos theta is equal to 0, and that will mean that theta must be pi over 2. When x is equal to 2, that means r cos theta is equal to 2. Since the number is so large, that means theta must be at its, cos theta must be at its maximum, which will be when theta is equal to 0. And so the bounds of x is equal to 0 to x is equal to 2 is the same thing as integrating from theta is equal to 0 to theta is equal to pi over 2. And so my bounds will now become, for one of them, I'll have 0 to pi over 2. Let's check out our y bounds. So for our y bounds, I'll be integrating from y is equal to 0, and this will be r sine theta. So theta must be, until y is equal to the root of 2x minus x squared. So to begin solving this, let's isolate let's get rid of this square. This will become y squared is equal to 2x minus x squared. Bring over the x squared, so y squared plus x squared, which we know as r squared, is equal to 2x. And then now we convert things to polar coordinates. So this is r is equal to 2, r squared is equal to 2r cos theta. Cancel out the r's, and we get r is equal to 2 cos theta. So we're going to be integrating from r is equal to 0 to r is equal to 2 cos theta. And so now when we write out our new region D in polar coordinates, this will become integrating from 0 to pi over 2, and I'm integrating from 0 to 2 cos theta. And those will be my bounds. And so when I write that out, it will be 0 to pi over 2, 0 to 2 cos theta. We found that the argument is going to be r, and then my area, so dA in polar coordinates is r dr d theta. So we've successfully converted it to polar coordinates, and now we need to just solve it. So we can simplify this to become 0 to pi over 2, 0 to cos theta, r squared dr d theta. We're going to integrate our r first, and that will become the integral from 0 to pi over 2 of r cubed over 3. For this, I just use the general rule that the integral of r to the power of a will be 1 over a plus 1 r to the power of a plus 1 if I'm integrating over dr. And so r plus 1 is 3, so it's r cubed over 3. But then I need to remember that this was a bounded integral from 0 to 2 cos theta. And that leaves a d theta. Okay. And then next up, what I am actually going to do is evaluate it. So it will be the integral from 0 to pi over 2 of 2 cubed cos cubed theta minus 0 cubed all over 3. So I'm going to pull out this 2 cubed and the 3 to become 8 over 3. This will be integrated over theta. The integral from 0 to pi over 2 of cos cubed theta is what that will leave over. And I'm integrating over d theta again. And then next up, I will use the fact that cos cubed theta is equal to cos theta by cos squared theta. And then I will use the identity that cos squared theta plus sine squared theta is 1. So I can say cos squared theta is equal to 1 minus sine squared theta. And so this will become 8 over 3 multiplied by the integral from 0 to pi over 2 of cos theta into 1 minus sine squared theta. And then I integrate over d theta. And then I'm going to use substitution in order to solve this. So if I set u as sine squared theta, this would mean that du is equal to 2 cos theta d theta. And I got this using, if I substitute t is equal to sine theta dt over d theta, is going to be cos theta, and I can just use the chain rule in order to find the derivative, and it will give me 2 by cos theta. And then I just moved over the du over d theta. And so that is what that gives me. And so if I put all of this in, I will get that cos theta is du over 2 over d theta. And so I can just put that all in to get 8 over 3, the integral from 0 to pi over 2, 1 over 2 because of this 2 here, multiplied by 1 minus u squared du. Because I would be integrating cos theta, 1 minus u, and then I just substitute d theta is du over 2 cos theta. So du over 2 cos theta, these two cancel, leaving 1 over 2, and that. And so that's how I got to that point. And so that is what that will leave me in. And then now that it's a lot simpler, I can just pull out the 1 over 2. So 8 over 3 by 2, which will become 4 over 3, the integral from 0 to pi over 2 of 1 minus u squared du. And then I'm just going to use integrating powers in order to figure that out. And that will become 4 over 3 into u minus u cubed over 3 from 0 to pi over 2. And once I calculate that, that will give me the simple answer of 2 over 3. But we can just do that together. So this will become pi over 2 minus pi cubed over 8 all over 3 minus 0 minus 0 cubed over 3. And this will give me 4 over 3 pi over 2 minus pi cubed over 8 by 3, so 24. And once I calculate all of that, I'll get the 2 over 3. And that's going to be it for this question. Oh, don't forget my apologies to change the integration bounds because of the substitution. Once I substituted the u, since u is sine squared theta, sine squared 0 is 0, sine squared pi over 2 is 1. So the integration bounds change here. Be very careful with that because you can easily forget to, as I have here. This will give me 1 minus 1 over 3 minus 0 over 3. And this will give me 4 over 3 into 1 minus 1 over 3, which will give me 2 over 3. And so finally, that will give me an answer of 8 over 9. 1 minus 1 cubed over 3, 2 over 3. So this will give me 8 over 9 as my final answer. Okay, on to the next question. We want to find the exact length of this curve. And so again, the general formula is the length of the curve evaluated from a to b is the root of 1 plus the derivative of that function with respect to x squared integrated over dx. And so obviously we're going to need to find this, and we're going to use some general rules to find it. So let's just write down all of those rules. The first one is that the derivative of f of x plus g of x is the same thing as if I took the derivatives independently. Additionally, I have that the derivative of f of x to the power of a will be 1 over a f of x to the power of a minus 1 multiplied by the derivative of f of x. And lastly, this is where this rule stems from, the derivative of f of g of x will be the derivative of f of x multiplied by the derivative of f of g of x. Sorry, this is supposed to be g of x here. And that's going to be it. And so, for our question, we want dy over dx, which is going to be d over dx of root x minus x squared plus the inverse sine of root x. So first up, we're going to use the first rule in order to separate them. We're just going to label that 1. And this will become d over dx, x minus x squared all to the power of 1 over 2, plus d over dx, the inverse sine of root x. Okay, next up, I will apply 2 to this one and 3 to this one. And so this will give me that the derivative of x minus x squared all to the power of 1 over 2 is going to be 1 over 2 x minus x squared negative 1 over 2 multiplied by the derivative of what is inside. And so that is going to give me 1 minus 2x. Finally, this will give me 1 minus 2x once I multiply them out over 2 into root x minus x squared. Okay, next up, I'm going to want to deal with this section. So d over dx sine negative 1 root x. And this is going to be equal to d over dx sine negative 1 root x multiplied by d over dx root x. And so I'm just going to treat this like it's any other value and put in what the derivative of the inverse sine is. And I just need to note that down here for you. The derivative of inverse sine x is 1 over root 1 minus x squared. And that's if I have x. And so now that I have root x instead here, let's write that down somewhere else. Okay, and so now that I have root x inside of it, I'm just going to use root x instead of the x squared here. So this will become 1 over root 1 minus root x squared plus the derivative of square root x, multiplied by the derivative of square root x, which is 1 over 2, x to the negative 1 over 2. My apologies. Yeah, So this is just going to give me 1 over 1 minus root x squared off of what I showed you before. And this is just going to give me 1 over root 1 minus x once I evaluate root x squared, which is just x. And so now when I put that all together, because I need to add the two of them as I've seen here, I will get that dy over dx is equal to 1 minus 2x over 2 root x minus x squared plus 1 over root 1 minus x, I believe. Sorry, just the last clarification on this, my initial formula was correct. This will give me 1 over root 1 minus x, as we said, multiplied by 1 over 2 root x. And so here I will write that. Okay, and then I'm going to first expand this out. So I can just multiply the root x by everything here. And this will become 1 minus 2x over 2 into root x minus x squared plus 1 over, I'm going to keep the 2 outside and then multiply what are inside the square roots by each other. So x by 1 minus x will give x minus x squared. And so I can see I have the same denominator here, so I can just add these two and it'll become 1 minus 2x plus 1 over 2 over, multiplied by the square root of x minus x squared. This will give me 2 minus 2x over 2 root x minus x squared. I can see a common factor of 2 here, so I'm just going to cancel it and leave me with 1 minus x over the square root of x minus x squared is what I will be left with. Okay, and then now I can just take care of that radical. And so this will become 1 minus x into the square root of x minus x squared. And these two will cancel the square root, leaving x minus x squared. And then now to simplify this further, I'll note the common factor here is x. So 1 minus x into root x minus x squared over x into 1 minus x. These two can cancel. And that will leave me with root x minus x squared over x. I'm going to try and put that x inside. And so that will be root x minus x squared over x squared all together. And then I can pull out the common x to simplify it as far as I can over x squared. And these two will cancel. And that will finally leave me with the root 1 minus x over x as dy over dx. So now that I've found it, it's going to make all of this a lot easier. Before I put it into my formula, I'm going to need to find my integration bounds, and they will be dependent on the domain of what our y is. So let's look at the pieces of y. So the domain of root x minus x squared is just that x minus x squared needs to be greater than 0, so x needs to be greater than x squared, which means 1 needs to be greater than x, according to this one. And then the domain of the second part just states that x is between 0 and 1 for this one. And so my final domain of y itself will be that would be that the function lies between 0 and 1. So my a will be 0 and my b will be 1. And then now I can put everything into my formula. Then integrate from 0 to 1, root 1 plus dy over dx squared. Dy over dx is 1 minus x over x, the square root of it, so it's squared, we'll just leave what's inside. So 1 minus x over x dx. And then let's simplify this. Let's treat 1 as x over x. So 0 to 1, the root of x plus 1 minus x over x dx. These two x's will cancel, and it'll leave the integral from 0 to 1 of 1 over square root x dx. And this can just be stated as integral from 0 to 1 of x to the power of negative 1 over 2 dx. And I actually know how to deal with this one, because we know that the integral of x to the power of a over dx is 1 over a plus 1, x to the power of a plus 1. So I'm just going to apply that here. And it will give me 1 over negative 1 over 2 plus 1 is just going to give me 1 over 2. X to the power of negative 1 over 2 plus 1, which is 1 over 2 again. And remember your integration bounds. So this will be 2 root x evaluated from 0 to 1. And that will give me a final answer of 2 root 1 minus 2 root 0. This doesn't mean anything. This just gives me 2. And that's going to be it for this question. Okay, next up I want the derivative of arc cos of x. Okay. So I have y is equal to arc cos x. And what this means is that cos of y is equal to x. And so to find this, I'm going to take the derivative on both sides. Okay, and the derivative of, just as a general rule here, I know that the derivative of cos of a function of x is equal to negative sine of the function of x multiplied by the derivative of f of x. And so in my case, when I apply that to the formula here, I'll get negative sine y multiplied by dy over dx. And remember, dy over dx is what I'm looking for, is equal to 1. And so this will mean that dy over dx is equal to negative 1 over sine. And then I'm just going to put in what my y is, and it is arc cos x. And so I'm going to need to simplify this further before I leave it in its final answer form. And how I can do that is I will make note of the fact that sine squared x is equal to 1 minus cos squared x. And so sine x is equal to root 1 minus cos squared x. And so I'm just going to replace the sign here with, so what I've gotten here, I'm going to plug it in here. And this will leave me with dy over dx is equal to negative 1 over the square root of 1 minus cos squared, and then as my x, I'm going to put in that arc cos. And then lastly, I need to note that cos of, so cos of arc cos x is equal to x, because arc cos is the inverse function for cos. And so the function of the inverse function is just whatever the input was. And so this will mean that cos squared of arc cos x is going to give me x squared. And so that's what I'm going to put in here. And this will leave me with dy over dx is equal to negative 1 over the root of 1 minus x squared. And that is going to be your final answer. Okay, on to the next question. We are looking for the derivative of secant x. And for this one, we're going to be making use of the quotient rule. So first off, we need to know that secant x is 1 over cos x, and that the derivative of f of x over g of x is going to be this. All over g of x squared. And so we'll get that d over dx of secant x is equal to d over dx of 1 over cos x, and then we're going to use our formula to figure out what that is. And so for our function, f of x is equal to 1, so the derivative of that is equal to 0. G of x is equal to cos x, and so the derivative of that is equal to negative sine x. I'm going to plug this all back into this formula, and this will give me that d over dx of 1 over cos x is going to be 0 multiplied by cos x minus 1 multiplied by negative sine x, all over cos squared x. These two negatives will cancel each other, so I'll be left with sine x over cos x by 1 over cos x, because I just split the cos squared. And this will give me tan x secant x, and that is what the derivative of secant x is going to be. And that's it for this question. Okay, next up, we want to prove the formulas given for the derivatives of the hyperbolic functions. So let's just run through all of them. And so for all of them, I'll be using a couple of rules. First off is that the derivative of f of x plus g of x is equal to the derivative of f plus the derivative of g. So it's the same thing as if I took the derivatives independently. 2, the derivative of a constant multiplied by f of x is the same thing as if I pulled out that constant. And lastly, the quotient rule. And this will all be over g of x squared. And so for our first one, we're going to look at what it actually is. So cos hx is equal to e to the power of x plus e to the power of negative x all over 2. And so to deal with this, we will first use rule 2 to pull out that 1 over 2. So we will get d over dx of e to the x plus e to the minus x over 2 is equal to 1 over 2 d over dx x plus e to the minus x. And then we're going to use rule 1 to separate these. And this will give us 1 over 2 multiplied by d over dx of e to the x plus d over dx of e to the minus x. This one we know how to deal with. It's going to give us e to the x. This one we're going to use the chain rule. And what we're going to do is we will set u as negative x. du is equal to negative dx. Sorry, du over dx is negative 1. So dy over dx is equal to dy over du multiplied by du over dx. And this will give us e to the u multiplied by -1. So negative e to the minus x is what that's going to give me. And so this is e to the x, this is e to the minus x, but multiplied by -1. And so when I put that all back together, I will get that the derivative of my first hyperbolic function is equal to e to the x minus e to the minus x, because of this minus in front of it, over 2. And this we know as a hyperbolic function for sine x. So that's going to be sine hx, and that's going to be your final answer for that first one. Next up, we are looking for the derivative of the hyperbolic function tan hx. And you just need to remember that that is sine hx over cos hx. And so for this one, we are going to be using the quotient rule. So I have it listed for you up here, and we're just going to find the individual derivatives. We already know that g of x is equal to cos hx, and that the derivative of that is sine hx. Now let's go about finding the derivative of our f of x, which is sine hx. We can find that quickly applying the same rules. So e to the x minus e to the minus x over 2. 1 over 2 d over dx of e to the x. Minus d over dx of e to the minus x. And we already found this. This is going to give us minus e to the minus x and e to the x. And so as my final answer, these two minuses will combine to give me a positive, and this will give me e to the x plus e to the minus x over 2, which we saw initially as cos hx. And so they have a similar relationship to sine x and cos x of being each other's derivatives. And so f prime x is equal to cos hx. Okay, now combining all of these and applying the quotient rule, this will give us, so f prime x, so cos hx, multiplied by g of x, so by cos hx2, so that's squared, minus this multiplied by this, so sine h squared x all over cos h squared x. And then to simplify this down, we're going to use an identity that they've listed here for you. And the identity is simply that cos h squared x minus sine h squared x is equal to 1. And so we're going to replace the numerator here. And this will become 1 over cos h squared x. And that is simply going to be secant h squared x. Okay, next up, for our third one, we are looking for cosecant hx, which is 1 over sine hx. Just ensure that's what we're finding. Okay, and so we're going to use a similar rule as to what we had before with the quotient rule. So f of x is 1, the derivative of that with respect to x is 0. G of x is sine hx, and the derivative of that is cos hx. And so when you put that all together using the quotient rule, this will give us 0 multiplied by sine hx minus 1 multiplied by cos hx, and this will all be over sine h squared x. Okay, and this will give me negative cos hx over sine h squared x, but I'm going to choose to separate that. so that I can write it as this product. And these two have well-known identities. This is negative cotangent hx multiplied by cosecant hx. And that's going to be it for this one. And then next up, we are looking for secant hx. You just need to remember that that is 1 over cos hx. And so similarly, we will apply the quotient rule. And so we have f of x is equal to 1, so the derivative of that is equal to 0. G of x is equal to cos hx, so the derivative of that, as we found earlier, is sine hx. And so we're just going to put that all in, and we'll get 0 by cos hx minus 1 by sine hx, and that will all be over cos hx squared. And this will give me negative sine hx over cos hx multiplied by 1 over cos hx. And this will give me negative tan hx multiplied by secant hx. And that's going to be my final answer, because this is secant h and this is tan h. And then next up, I think it is cotangent h. And so is equal to d over dx of cos hx over sine hx. Okay, and so for this last one, again, we're going to apply the quotient rule. F of x is cos hx, and so the derivative of that we found earlier, it'll be hyperbolic sine. G of x is hyperbolic sine. The derivative of that, as I said earlier, is going to be hyperbolic cos. Put that all together, and we will get hyperbolic sine by hyperbolic sine, so squared, minus hyperbolic cos by hyperbolic cos, so squared. And this is all going to be over sine hx squared. And so remember our identity from up above, the last time that we saw this, in which we stated hyperbolic cos squared minus hyperbolic sine squared is 1. And we can see something similar here. We have negative hyperbolic cos squared minus hyperbolic sine squared all over hyperbolic sine squared. And so this is going to give us 1 according to this identity. So this is negative 1 over hyperbolic sine squared. And this is negative hyperbolic cosecant squared. And that's going to be it for this question. Next up for this question, we're evaluating an integral. And so if we put in our r, we are integrating x from 0 to 2 and y from 0 to 3 of y e to the x y dy dx. Okay, and so for this one, we'll make the substitution. U is equal to xy. So du over dx is going to give us y. So we get that dx is equal to du over y. And what we're actually going to do here is we're going to integrate with respect to x because of that. first. And so this will actually become the integral from y is equal to 0 to y is equal to 3. Integral from x is equal to 0 to x is equal to 2 of the same stuff. Okay, and so now when you put everything in, you'll get the integral from 0 to 3, 0 to 2, y e to the u, du over dy, du over y, and then multiply by dy. These two obviously cancel each other out. This will become the integral from 0 to 3. And when x was 0, u was 0, and when x was 2, u was 2y. And so this will become 0 to 3. We know that the integral of e to the u is e to the u. And this will become from 0 to 2y over dy. And so let's put that in. 0 to 3, e to the power of 2y minus e to the power of 0 all over dy. Okay. And so we can now split this integral because of the rule that the integral of f of x plus g of x all over dx is equal to the integral of f of x over dx plus the integral of g of x over dx. And so we're going to use that to split this up. E to the power of 0 is 1. And so this will become the integral from 0 to 3 of e to the 2y dy minus the integral of dy from 0 to 3. Okay, and so again, I'm going to make the substitution. U is equal to 2y. So then I would be integrating from 0 to 6 instead. Du over dy is going to give me 2. So dy is equal to du over 2. And then I'm just going to put that all back in. I already know this is going to give me y. So this will be 0 to 6 e to the u du over 2 minus y from 0 to 3. This is going to give me 1 over 2 multiplied by e to the u from 0 to 6 minus 3 minus 0. And this will give me 1 over 2 e to the 6 minus e to the 0 minus 3. And this will finally give me e to the 6 minus 1 all over 2 minus 3 as my final answer. And that's going to be it for this question. Okay, next up we're looking for the gradient vector field of f, and we would like to sketch it. And so you will find vector fields that can be expressed as the gradient of scalars. And for example, an example of a vector field that's like this is the gravitational force, and it is going to be the negative gradient of negative gmm over r. And this is what you usually call V, the potential. And so F is usually called the potential, and it is just a scalar. Okay, and so once I do that, this will become just the gradient of gmm over r. And this is how we get to the force of gravity equation. You also have the same thing going on for electricity. It'll be the negative gradient of V, and that would be the negative gradient of 1 over the permittivity of free space multiplied by Q over R. Additionally, the magnetic field is also like this. When you take the gradient of a magnetic field is how you get a magnetic force, which is why you need the magnetic field to have a gradient for it to cause a force. And so that's just a brief explanation of what we're doing here. And so we need to recall that this is equal to d over dx, d over dy. And so now when I take the gradient of a vector field, what I will get is f, the derivative with respect to x in the I component, plus the derivative with respect to y in the j component. And so let's go about finding each of those. So if f is equal to f is equal to x minus y squared over 2. Let's go about expanding that, and this will become x into x minus y into x minus y all over 2. So we get x squared minus xy minus xy minus y squared over 2. And this will just give me x squared minus 2xy minus y squared, plus y squared, all over 2. And this is going to be my f. And so I go on to find the partial derivatives. So fx df over dx is equal to, I'm just going to pull out that 1 over 2. And then multiply it by the derivative of x squared minus 2xy plus y squared. So this y squared will have it won't give us anything because it doesn't have any x dependent, and so I'm just going to be focusing on these two, and that will give me 1 over 2, 2x minus 2y, and that is just x minus y. Okay, next up, I do the same thing, but the partial derivative with respect to y. And this will give me, again, pull out the 1 over 2, x squared minus 2xy plus y squared. Okay, and this will give me, again, for this one, x squared gives us nothing because it has no y dependence. And this will give me negative 2x plus 2y. And then I'm going to cancel out the 2's, and this will leave me with y minus x, so the negative of that, which means that the gradient of my vector field, the gradient of my potential is going to be x minus y in the I component and y minus x in the x component. And this is going to be my final answer. And so if you go about sketching that, what you'll get is this vector field that's shown in the answer. And so we can see that, like, for example, at the position 2, 0, that means, so at 2, 0, so x is, at 0, 2. So this is going to be negative 2, and then y minus x, 2. And that is the small vector that is shown here. And so if you just go about checking each of these individual vectors, you should get the correct y and x in order to give you the vector that you see there. And that's it for this question. And next up, I'd like to integrate sine squared x. And so I'm going to use the same method that I did for cos squared x. And I'm just going to note that sine squared x is equal to 1 minus cos 2x over 2. And so, and then secondly, I'll use that the integral of f of x dx is equal to the integral of g of x dx if f of x is equal to g of x, as we showed before, which is why I can use this. And lastly, that the integral of some constant dx is equal to kx plus c. And then the integral of a fx dx is equal to a multiplied by the integral, like that. Okay, so we found that sine squared x is equal to 1 minus cos 2x all over 2. We're going to pull out that 1 over 2. 1 minus cos 2x dx, and then we're going to separate this as we did before. Okay, this one is quite straightforward. This one isn't as straightforward. We're going to use substitution. And so if we set u as 2x, then du over dx is 2. So dx is du over 2. And so that means that the integral of cos u du over 2 is going to be 1 over 2 multiplied by the integral of cos u over du. The integral of cos u we know is sine u, so it'll become 1 over 2 sine u, which is 1 over 2 sine 2x. And so when I put that all back in here, I know that the integral of 1 dx is just x. This will become 1 over 2 x minus 1 over 2 sine 2x. And then I'll put the plus c outside of all of that. So this will become x over 2 minus sine 2x over 4 plus c. And that's going to be my final answer for this one. Okay, lastly, we want to simplify cos of inverse sine of x. Okay, so for this one, so let's begin talking about inverse sine of x. Let's say it's equal to theta. This means that sine theta is equal to x. Okay, additionally, this would also mean that sine squared theta is equal to x squared. Now we have an identity for this where we know that sine squared theta plus cos squared theta is equal to 1. So I'm just going to move that over to get sine squared theta is equal to 1 minus cos squared theta. Okay, and then I'm going to put that in place of sine squared theta. So I have 1 minus cos squared theta is equal to x squared, which will mean that cos squared theta is equal to x squared. So is equal to 1 minus x squared. And then I'm just going to take the square root to find cos theta. Root 1 minus x squared, and it's going to be positive or negative. And so I have that inverse sine of x is equal to theta, and that is going to be the inverse cos of positive or negative root 1 minus x squared. Okay, and so now instead of having this version of theta within the argument, I'm instead going to have this one because I can easily deal with cos and inverse cos because the two will cancel each other out due to the inverse relationship. But I additionally need to note that for sine minus 1x, it is going to lie in between negative pi over 2 and pi over 2, and it will always spit out something that, so the cos of this will always spit out something that's greater than 0. And so I'm not going to be able to put in this negative, and what's actually going to happen is I'll put in only the positive one. You'll see why at the end, and it'll relate back to this point. And so my cos inverse sine of x will become cos inverse cos of positive or negative root 1 minus x squared. Cos, inverse cos will just give me what the argument is inside. And so this will just leave me with positive or negative root 1 minus x squared. But as I said, because sine, inverse sine of x is between negative pi over 2 and pi over 2, that means that cos of inverse sine of x should always be greater than 0. And so this means that this will cancel out the negative option we have for the square root. And my only answer will be root 1 minus x squared, positive root 1 minus x squared. And that's going to be it for this question. Okay, and those are all the questions I have for you today. I hope you enjoyed today's Q&A. If you'd like to be notified of when we do post, be sure to hit the subscribe button. If you'd like to be able to post questions of your own, be sure to check out the links in the description so you can get access to the OneClass page where we do source these questions. This has been Marlyn from OneClass, and I hope to see you next time.